All right, so I'm very happy to introduce Jay here. I will not try to pronounce his name. So he's at NYU Shanghai, and he's visiting me for a few weeks. So anyone who wants to talk to him is welcome to contact him. And Jay is kind of a rising superstar. He's gotten an infinite number of papers in the last computational geometry conference. Probably not infinite because there's an upper bound on the number of talks, but so he's worked on various interesting topics, and he's going to tell us about one of them today. So I'll let him speak.
Okay, thanks for the introduction. Today I'm going to discuss some matching problem in geometric setting. So
I don't think the laser works on that screen very well. So
okay. So
you may have to use the finger.
yes, that's fine. Let me. Okay. So let's start with some basic definitions. Suppose there is a graph here, and a matching in this graph is just defined by a set of disjoint edges. But by disjoint, I mean their endpoints do not share any endpoints. And this is usually called a one-to-one matching because, as you can see, you use those edges to match those points, and each point is at most matched to one other point. Right? So this is why it's called one-to-one matching. It's just represented by a set of disjoint edges. And you can distinguish two types of one-to-one matching. So the first type is called perfect one-to-one matching. That means in your graph, every vertex is matched to another vertex. So here, as you can see, those edges cover all the points, so it's perfect. The other type is non-perfect or imperfect one-to-one matching. So as you can see, some points are left; they don't have any other point to match. Okay, so this is one-to-one matching, and because you have one-to-one matching, you can also define the so-called many-to-many matching. So then, for a many-to-many matching is just a set of edges, because here you are matching vertices using edges, but you don't have the restriction where every vertex is only allowed to match to one other vertex, and every vertex can be matched to multiple other vertices. So you just select a set of edges that each is just a many-to-many matching. And again, you can distinguish perfect many-to-many matching and the imperfect ones. Perfect means each vertex is matched to at least one other vertex. Okay. And so in this situation, as you can see, it's perfect because every vertex is matched. And also in some other cases, in this case, although you have a lot of edges here, as you can see at this point, this vertex is left, so it's an imperfect many-to-many matching. Okay, so far. Okay. Okay, so we consider matchings in not only a graph, but it's a graph with edge weights. So for every edge, you have a positive number, real number, or integers, whatever. So it is the weight of that edge. And with this weight, what kind of question you can ask? So of course, one question you can ask is, can you find a perfect matching with minimum total edge weight, right? So as you can see, you can ask the computational question. So for one-to-one matching, you can ask the question where you want to find a one-to-one matching with minimum weight, which is called minimum weight one-to-one matching problem. And again, for many-to-many matching, you can also ask the same question. Can you find a set of edges which cover all the vertices in your graph, whose total weight is minimized? Okay, so this is these are all classical problems in computational geometry. Oh, sorry, it's actually in algorithmic graph theory. Okay, so today we are not going to discuss the abstract graph problems, but we should have some geometry, right? So we consider graphs that are defined in a geometric setting. So these graphs are called geometric graphs. Let me first give you one simple example. So suppose you are given a set of points in the plane, say S, and those points are just the vertices of your graph. And then you connect each pair of points using an edge. Then this gives you nothing but a complete graph. So far, there's no geometry there. But when you define the edges, the weight of edges, if you use the distance between the two endpoints, then it naturally gives you the weights for every edge. So this is if your edge weights are defined in this way, let's call it a geometric graph defined, say, by points in 2D. Of course, you can also use points in higher dimension to define geometric graph. But the limit of this representation is that you can only define you can only define complete graphs. Right? So there is another more expressive way to define geometric graphs, which can give you like more types of graphs. Is the following way: you can give colors to the points. Now, again, I have points either in the plane or in higher dimensional Euclidean space, and where each point is associated with a color. So these are, you have 3 red points, 2 yellow points, and 1 blue point in this example. And then when you connect points with edges, you only connect those with the pairs of points with different colors. So in this case, your graph looks like this. You don't have an edge here because these 2 points have the same color. You don't have edges here because all of them have the same color. So you only connect the so-called like bichromatic pair of points. And again, the weights are just the Euclidean distance or any other measure or any other like distance under other metric. So in this way, you have a more general type of geometric graph. So you can call it a color geometric graph. Okay, so our task is just to solve this problem called geometric many-to-many problem. We want to solve the minimum weight many-to-many matching problem in a geometric graph. So in this problem, we are just given a set of colored points and colored points in some Euclidean space, which defines a geometric graph. And then I just want you to compute the minimum weight perfect many-to-many matching of this graph. So one example, if I give you such points, you just find such a many-to-many matching, which minimizes the total length of the edges. Okay, so this is the problem. So far, any questions?
So there's no, when you're doing the matching of many-to-many, there's no constraint on what you call a matching, except the fact that every point has to be at least connected to one other point.
Yes.
And then there's the color condition.
Yes, yes. The color condition defines the edges. For example, you cannot connect this one with this one because they have the same color.
Okay.
So you consider only metrics, so you don't consider like say square root in this. People like to
Square root.
which is not metric.
I'm not sure. So, of course, the most natural one is the Euclidean distance, right? And when we discuss the result, we will mention that our algorithm also works for other metrics like L1 metric or like LP metric. I'm not very sure whether it works for square distance or not. Yeah, but this is a good question.
Yeah, because usually from Rassmann theory, people may consider square root.
Okay.
One
Yeah, I need to think about it more carefully to see. Okay, so this is the problem. And then let's look at some previous results on this problem. So in 1997, this problem was introduced. And then the problem in 1D, which should be very easy. And it's known to, you can solve the problem in n log n time, where n is the number of points. And then the problem in 2D already becomes tricky. So for exact algorithm, the only known algorithm is requires like n squared polylog n time to solve. And if you want the approximation algorithm, so is everyone here familiar with approximation algorithm? So basically, if you want a 1 plus epsilon approximation algorithm, so that means you want to compute a perfect many-to-many matching whose total length is not longer than 1 plus epsilon times the best answer. So then that requires so if you want an approximation algorithm, you can do it in roughly like n to the 1.5 time. And all these problems are known to be.
Can I just ask just the notation? What does the O sub epsilon mean?
Okay, good question. So here, the big O notation hides some constant, right?
Right.
So that means that constant depends on epsilon. So it might hide a constant, say,
Sure.
1
Sure.
over epsilon.
Sure.
How it depends? Do you remember?
This work, I think the dependence is polynomial, it's some 1 over epsilon polynomial. But later when we see like our new algorithm, it's actually very bad. It's exponential. So, okay, I should mention that all these problems are, so the minimum weight, perfect many-to-many matching problem is polynomial time solvable in any graphs, not only geometric graphs. So you can use Hungarian algorithm to solve it in n cube time. And because that problem is, you can reduce it to minimum weight 1-to-1 matching. And then minimum 1-to-1 matching is known to be polynomial time solvable. And using this algorithm, you can solve the problem in any dimension in n cube time. But it's, of course, it's slow. And by this result of Duan and Petty, you can obtain a quadratic time approximation algorithm. Again, this works for general graph, therefore for any geometric graph, but it requires quadratic time.
So that means this when G5 higher, those the result it actually follows from the
No.
no.
So this is exact algorithm is n
Ah,
squared.
exact
Here, yeah, here is n cube. You need,
So exact is very important.
yeah. Then approximation algorithm is n to the 1.5. It beats this n squared.
So for exactness, we have to pay logarithm, right?
Yes. Well, yeah, there are
Log
some
square.
polynomial here. I think it's log square and not very bad. Okay, so as you can see, like even in 2D, the time complexity is still not very satisfying. Still, for even for approximation, you need n to the 1.5. But on the other hand, if you consider 1-to-1 matching, then it's another story. So it was known that if you, at least for the approximation algorithm, it was known that you can do near linear time. So here, what is near linear time is just n times polylog n time in any fixed dimension. So this is 1-to-1 matching. So again, you have a geometric graph, you want to compute the minimum weight 1-to-1 matching. And it was known that you can have,
But it will be perfect, right?
it's perfect. So
You need
imperfect doesn't make any sense because you just don't take any edge.
but asking what there is.
Now over here,
But sometimes there is no perfect matching.
So you are given I think the same set of if you okay, so first this is this algorithm is known as for graphs with 2 colors, and those 2 colors should have the same number of vertices. Then that guarantees you to have
No, it's not
perfect.
guaranteed. Guaranteed.
It guarantees right because you have a
Full.
full bipartite graph. And I think so. There are 2 variants of the problem. Both of them admits near linear time approximation algorithm. One is you have a complete bipartite geometric graph where both sides have the same, like parts have the same size. The other variant is just like you have a complete geometric graph with even number of vertices, and then you want to find a perfect minimum weight, perfect 1-to-1 matching. That variant is also admits 1 plus epsilon near linear time algorithm.
And what can you explain the idea in one line? What is the idea behind it?
Oh, okay. It's not that easy. So if you are familiar with some tools in computational geometry and in graph theory, so they use the idea of chord tree, and then they use chord tree to help So first they run the general, are you familiar with the general like matching algorithm? So so first this one-to-one matching problem on any graph is solvable in polynomial time, but that polynomial is large, the MQ time. Then they somehow explore the geometry of the problem. They use some geometric data structure, essentially some chord tree, to help speed up the matching algorithm. So that's that's what I can tell. So yeah, actually there are a lot of work in this problem. Okay, now the question is, since we can do for one-to-one matching, we can have one near linear time approximation algorithm. What about geometric many-to-many matching problem? Does it also admit near linear time 1 plus epsilon approximation algorithm in any fixed dimension? Okay. And our new work solves this problem.
So there is a result with the square, right? And now we want to.
Yes. So square is currently you can apply this general algorithm to get square. Approximation in 2D you can get n to the 1.5. Okay, so this is the first work we have. We show that you can do it in n log n time actually. So I give you the instance in any fixed dimension D, then I can give you 1 plus n approximation solution in n log n time, where here you have something depends on epsilon hidden here. And this algorithm actually works for any LP metric, not only for Euclidean distance. And possibly it also works for square distance. I'm not very sure. I need to check the details.
Do you need a P maybe just any Minkowski metric? No, any Banach metric.
So sorry.
You know Banach metric or Minkowski metric.
What
You define convex self-symmetric convex body of the unit ball, and it's called Banach metric or Minkowski metric. So probably all that works for them.
Probably, I'm not sure. Okay, so first notice
So
that
what's the role of color in this one problem? In this problem,
you don't have any
No
restriction on
colors
the color.
here, yeah.
You can give me any points with any color.
Yes.
Yeah. Oh yeah. So
no, I mean, does
this
this is a theorem for uncolored graph vertices?
no for color.
Even for color.
Even for color. Yeah. So okay, the good thing for this theorem is it works for any coloring of the points.
I see.
So yeah, not a constant, not just a constant number of colors or all different colors. You don't have any restriction on coloring.
And this all epsilon it depends from all these settings, number of colors, from dimension, from everything. This epsilon, all this epsilon.
This epsilon is the yes, no, it doesn't depend on the number of colors. It depends on the dimension as well. Dimension is also a fixed number. So what I can tell is it's a very bad number. It's 2 to the 1 over epsilon to the d, so something like that.
But no.
Yeah, but it's if you view epsilon as a constant, d as a constant, what's hidden here is something relative to epsilon. Okay. So first notice that this is actually tight. This n log n is tight, because even in 1D you cannot expect any algorithm better than n log n. So there is a reduction from set identity to one-dimensional problem. Okay, and of course our running time is doubly exponential in epsilon, actually in 1 over epsilon, which is bad. And another surprising thing is the approach of this result is entirely different from all the previous algorithms. So the previous algorithms for geometric many-to-many matching uses matching algorithms, so geometric data structures to speed up matching algorithms, right? Including the one-to-one matching. But as we will see, like in this algorithm, you don't have any matching algorithms. You just use some geometric tricks. So this is the first result. And then in a follow-up work, well, we have a somehow improved algorithm for the problem. But now we improve the running time. Now it becomes polynomial in 1 over epsilon. But then we don't, so we have, so this is a more restricted in the sense that we can only solve the bichromatic case. We can only solve the case where you have two colors. You don't have one more colors. But this result generalizes to any metric space with doubling dimension D. This includes all the like the LP metric so for the problem. I'm not going to discuss what you mean by doubling dimension D. It's something. So of course, you know, is there any easy way to explain that?
Well, you promised not to explain it.
Okay,
So.
sure.
Okay, keep your promise.
So, okay, and also this result extends to some more general geometric matching problem where you compute a many-to-many matching, and there is another so constraint saying that for each vertex P, you want it to be matched at least some number of times. So this is a more general problem, and the algorithm actually generalizes to this setting as well. But I'm not going to discuss this algorithm today. I'm going to discuss the previous one because this algorithm, the technique is goes back to using geometric data structures to speed up matching algorithms, which I found not that exciting. And also the algorithm itself is complicated. But this one is relatively simple, so I'm going to discuss this algorithm.
Thank you.
Yeah. Okay. So so far, any questions?
So far, so good. You've made a very clear explanation.
Okay, so now let's briefly discuss the first analog algorithm. So let's focus on the plain case and with Euclidean metric. And the generalization is not too difficult. Okay, so here, let me introduce some notations. So we have S, the set of colored points in the plane. Let's use GS to denote the geometric graph defined by S. Okay. E of GS, the set of edges of GS. Then
Sorry, GS, by the geometric graph defined by S, you mean the complete graph?
no. So
Oh, you're giving color
yeah,
points, yes.
you have
Yes, right.
you want to
Given by the
measure
color.
yeah,
Fine.
different colors. Okay, edge set. Then for each subset of edges, I use this cover E of E, meaning that the points or the vertices covered by E. So meaning that you take the endpoints. It's a subset of S, which is the endpoints of the edges in E. Okay. Then for each edge, I use this notation to denote the weight of the edge. So it's just the Euclidean distance. Okay, so first let's consider a very simple question. If you have a point, right, in S, and you want it to be matched with some point, then which point you should choose? Of course, it should be the point closest to this point P, but which has a different color than S, right? Than P, right? So for that point, I give it a name. I say it's a nearest foreign neighbor, NFN of P. So in this example, if you have a P, right, what is its nearest foreign neighbor? It's this black point. It's not this blue point, although it's closer to P, but it has the same color with P. Okay, so this is the notion of nearest foreign neighbor. So when you only consider one point, and if you want to match it, of course, this is the best choice for you to match it. You just connect it to the nearest foreign neighbor. Okay, so for each point P, let's denote by phi of P, the distance between P and its nearest foreign neighbor. Now, our first step is we want to somehow transform the original problem to an equivalent problem, which seems easier to handle. So what is this equivalence? So first consider like in our original problem, where we talk about the solution for the many-to-many matching, we want it to be perfect, right? We want it to cover all the points, all the colored points. So therefore, there is some restriction on the solution you are looking for. So not every subset of edge is a solution, right? But now I'm going to convert the problem to an equivalent version where every set of edges can be a solution. So this is a penalized, I call a penalized version of the problem. So I give you that graph, and then suppose I somehow allow the solution edges to not cover all the points in S. I can have some points that are not covered by my solution edges. However, for every uncolored point P, I have to pay a penalty, which is equal to phi of P, where phi of P is just the distance from P to its nearest neighbor, foreign neighbor. Okay, so essentially, so what we want is in this version of the problem, we want to compute a set of edges, which does not necessarily cover all the points, but its cost will be the total length of the edges you have, plus all the points that are, for all the points that is not covered by your edges, you add their penalty. So first, so some example, if you take this as your solution, then you should pay the length of these three edges plus the penalties for A and B. Okay, so then I will explain why these two versions are actually equivalent. It's not very difficult to see. So, so first, let's look at the original problem. Any solution of the original problem is, of course, the solution of the penalized problem, because and the cost is the same because you just want to pay the length of the total length of these edges. You don't have any unmatched point, so you don't have any penalty. Right? So from this one to this penalized version, it's clear. But how can you do the other direction? Suppose you have a solution for penalized version of the problem. Of course, it's not a solution for the original problem because you have points that are not covered. However, what you can do is you just connect them to their neighbor. So you will get a solution. What is so the cost here is the total length of these edges plus the penalties for the uncovered points. Then the total cost here, it is at most the total length of the edges plus these edges, which is just the penalties of the points. And as you can see, if you have an optimal solution here, you can convert it to an optimal solution for the penalized version. And also, if you have an optimal solution for the penalized version, you can convert it to an optimal solution of the original. So actually, the two versions of the problems are equivalent. Okay, so the benefit of doing that is, so in original problem, not every set of edges form a solution. But now in this penalized version of the problem, you don't have any restriction on the feasible solutions of the solution of the problem. So the only thing that you care is the cost of your solution. Right? So this gives you this makes us like more, it's now more convenient to handle this version of the problem. Okay, so from now let's just focus on the penalized version of the problem. So I will make a very simple but useful observation for the problem. And notice that look at an edge between the two points, U and B. And I claim that the length of this edge must be greater than or equal to both the penalty of U and the penalty of B. And this is very clear because this is the distance from U to its nearest foreign neighbor. This is the distance from B to its nearest foreign neighbor. So you must have this inequality. So then, from this, we have a very simple fact. So imagine that now you have a solution, which is a set of edges, right? And you have a subset of that solution, the E prime. So I want to see what happens if I remove E prime from E. So what happens is the following. So if you remove E prime from E, then first the total length of of the edges decreases. Right? So you should remove, for the cost of this set, you should remove the total length of the edges in E prime. However, your cost can somehow increase because some points becomes uncovered, unmatched, if once you remove these edges, right? So that means you might need to pay for those unmatched points. So that can, so first your cost will decrease because of the removal of these edges. Then your cost will increase because you have additional penalty to pay. However, if you look at every edge in E prime, if you remove it, say this is one edge in E prime. If you remove it, the cost decreases by the length of E. And in the worst case, you need to pay for the penalties of U and V. But both of these penalties are at most E. So that means the penalty you pay is at most 2 times E. Right?
Mhm.
So that means if you remove one edge from your solution, the cost of the increase of your cost is at most the length of E. So therefore, the cost of E minus E prime is smaller than or equal to the cost of E plus the total length of the edges in E prime. So this is a bit, so this inequality is a bit counterintuitive, because usually when you remove edges from your solution, your cost should decrease by this amount. But now in this problem, when you remove, your cost can increase, but can at most increase by this amount, by the total length of the edges you remove. And this turns out to be a very important inequality, which is used in our algorithm. Okay, so so far any questions? Good. So now in what follows, I will first consider an ideal case, and then I will consider like how to reduce to this ideal case. What is the ideal case? So look at the 5 values, in other words, which are the penalties of the points. Let's assume like the smallest penalty and the largest penalty, if you compare them, they are somehow similar to each other, in the sense that the ratio of the smallest one to the largest one is bounded by some constant depending on epsilon. Of course, this is not necessarily the case at the beginning, but we will show we can somehow reduce to this case. And in what follows, let's just discuss how to solve the problem in this ideal case. And then if we have time, we can discuss how to reduce to this ideal case. So the ideal case is all the penalties are similar to each other. Okay, let's assume we are in this ideal case. All the penalties are similar. So you define the smallest penalty to be phi minus, the largest penalty to be phi plus. Okay, then by assumption, this phi minus, you can, for convenience, you can just assume like phi minus is equal to phi plus, or they are just similar to each other. So how does this condition help? So the key observation is the following: if I have this condition, and if I have an optimal solution, then all the edges should have similar lengths. So let's see why this is the case. Look at one edge in your optimal solution, so U and V. Then we already know, like this inequality we know, so that the length of E must be greater than or equal to the penalties of U and V. But if it's an edge in your optimal solution, we should also have this inequality. We should have the inequality that the length of E is smaller than or equal to the summation of the penalties of U and V. Does anyone know why this is the case? It's not hard to see. If this is not the case, why not remove this edge from my solution? And at most, I will pay the penalties for U and V, right? If your length is greater than U and V, then you can just remove and pay the penalty. You get a better solution. So your solution is not optimal. Okay, so what is this number? This number is at least phi minus, right? So it's at least phi minus. What is this number? This number is at most 2 phi plus. So you have this inequality. Every edge in your optimal solution, it should be of length at least phi minus and at most 2 phi plus. But because phi minus and phi plus are similar, so all the edges in your optimal solution should have similar length. Okay, so good. Then this fact allows us to apply a simple grid shifting technique. So let's build a grid in the plane. for such a grid, where each cell is some square of side length 5 plus over epsilon. Okay. And then let's randomly shift this grid in the plane. Then you have, so suppose this is your optimal solution, which we denote by E opt. When you shift this grid in the plane, right? So as you can see, some of the edges is hit by the boundary of this grid, but some of the other edges are completely inside the cells. Right? Maybe let's call these edges intersecting the boundary of the cell crossing edges, and let's denote by E opt cross the subset of those edges. Now my question is, look at a specific edge. What is the probability that this edge will intersect the boundary of the grid? So notice that the length of this, I use the upper bound for the length of this edge in the optimal solution. The upper bound is 2, 5 prime. 2, 5 plus, right? Because the length of each one is 2, 5 plus. So the probability where each edge intersects the boundary of this cell is, okay, the side length of this cell is 5 plus over epsilon. So the probability that your edge intersects the boundary is something big O of epsilon, right? If this is, if you put like 0.01 here, so it's like 100 5 plus. So the probability that your edge intersects the boundary is some constant times 1%. Okay, so the probability an edge belongs to this set is big O of epsilon. So now you ask the question: if I consider the total length of these crossing edges, then by the linearity of expectation, the total length should be epsilon times big O of epsilon times the total length of all edges. Okay, so if you take the expectation of the total length of the crossing edges in expectation, it's equal to big O of epsilon times the total length of all edges in your solution. Right? So it's just an epsilon fraction of the total length. So why this helps? Because remember that we just argued that if we remove a subset of edges from our solution, the cost of the solution will increase at most the total length of those edges removed. Right? So now what if we remove these crossing edges? Let's say we just remove these crossing edges. The cost of the new solution might increase, but it only increases by the total length of these edges, which is big O of epsilon times opt. And that means this is a 1 plus big O of epsilon approximation solution. Actually, you have a big O here, a notation here, but if you are familiar with the approximation algorithm, the big O here is not important. Designing 1 plus big O of epsilon algorithm is sufficient. Okay, so that means you can have a near optimal solution where each edge is completely contained in one grid cell. Then why not just look for an optimal solution satisfy this condition? So now I want to look for a solution where all the edges in the solution are completely contained in these grid cells. So now I reduce to such a problem. Then the benefit of doing this is because each edge is completely contained in one cell, we can solve the problem in each cell individually. We can say, okay, what is the optimal solution for this cell? What is the optimal solution for this cell? And so forth. And then finally, we take the union. We solve each problem in each cell individually, and then take the union, which gives us a near optimal solution. Is everything clear? Okay, so now we reduce to the case where we want to solve the problem inside a small cell whose side length is 5 plus over epsilon. Again, so here inside it you have colored points, and you want some edges to cover some of these points, and for the other points you pay the penalty. So this is the problem. So now notice that the side length here, because your 5 plus and 5 minus are similar to each other, so you can understand it as some function of epsilon times 5 minus as well. Okay. So so far we have used the upper bound on the edges in your solution, in your optimal solution. Now we also want to use the lower bound.
One point that's confusing me. But 5 plus and 5 minus were defined using the whole original graph.
Yes.
And they involve the distance to the nearest neighbor and so on. But don't they change if I'm considering the graph restricted to a box?
Okay, good question. Actually, you don't change them. The penalty is always the same. So you don't change the penalty. It's not, so now the problem is not exactly the original problem.
I see.
Yes, the penalty is not.
You're using a slightly modified penalty.
Yes, yes. So so the penalty of this point is not equal to the distance from this point to its nearest foreign neighbor in the box. It might be smaller. I don't change the penalty.
Okay.
Value.
Okay.
So now I want to use the fact that each edge, not only the edges in the optimal solution. Actually, every edge has a length at most 5 minus. Sorry, at least 5 minus. Okay, how to use this property? Let's say this property tells us that if we move the location of each point a little bit, where the distance I move is at most epsilon times 5 minus. So suppose I randomly, arbitrarily move these points only a little bit within distance epsilon times 5 minus. Then what will happen? Of course, you change the solution a little bit, right? So for each solution, you change the edge length a little bit. But for each edge, you know that its length is at least 5 minus. If you only move epsilon 5 minus, so you only change the length of each edge by a factor of epsilon. So it's not too much. It's a number we can afford. Okay. So therefore, you can as you can verify, if you arbitrarily move these points within this distance, it doesn't match. It doesn't matter too much. Okay. Okay. So given this observation, what we can do is we can further partition this box into smaller boxes with side length epsilon 5 minus. Okay. Then, okay, we have these points. So notice that how many numbers of cells here? It's some constant because 5 minus and 5 plus, they are similar to each other. And so this is some constant depends on epsilon. Now we have points here. Right? What we can do is why not move all the points to the same location in each cell? Because we have shown that slightly move the points doesn't matter. So we just move all the points to the center of the small cells. And this only changes the cost of the solution a little bit. And then another observation is that all the points in the same cell must have the same color. The reason is very simple. So the side length of this cell is epsilon times 5 minus. It should be much smaller than 5 minus. If you have 2 points with different colors here, then their phi value is smaller, even smaller than epsilon 5 minus, which is impossible. Right? So 5 minus is the smallest phi value. Okay. So therefore, in each box, you should have the points should have the same color, and also their phi values should also be similar because they have the same color, and the difference between their phi values should be at most their distance. Given this, what we can do is we just move all the points to the center of that cell, those cells, and we slightly modify their phi values to the same number. So here we like manually change their penalty values to the same number. And also, as you can see, so after these modifications, in each cell, we have multiple points, but they are of the same color in the and in the same location, and they have the same phi values. So they can be viewed as multiple copies of a single point. Then how many points we have? It's only a constant. But we just have each point, we just have a mark saying that how many copies are there for this point. That mark can be large, but the number of different points is small, it's only a constant. And hopefully this can help us to efficiently solve the problem. And it is actually the case. We can now solve the problem using some technique called integer linear programming. We can form a integer linear programming to with only, so okay, first what is integer linear programming? Which is just a linear program where the coefficients and the solutions you are looking for are all integers.
Sorry, I'm just lost.
Yep.
So you essentially divide your square on number of small squares, which doesn't depend from B or C.
From what? Sorry.
So the number of squares depends only from epsilon,
Yes.
so it doesn't depend from anything.
Okay. So what is the side length of the large square? It's phi plus over epsilon. What is the size of the smaller square? It's epsilon times
okay,
phi minus. Because phi minus and phi plus are only differs by a factor depending on epsilon. So therefore the ratio of this one to this one is also some function of epsilon. Yes, so essentially here you have a constant number of points. They are totally the same, but you just have different copies of the points. So then you can form such a linear program with only constant number of variables, constant number of constraints. But what are so each point you have a label, which is the number of copies, but the number of copies becomes the coefficient of the ILP. So using known algorithm for ILP, we can solve it in log n time. And then this solves the problem when we have the nice assumption where phi minus and phi plus are similar to each other. Okay. So far, any questions? Yep.
Here, the n is.
N is again, so n is the total number of points here. The total number of points. So it's also the number of different points. You should also, so it's the original like total number of points, or just the total number of points in this box.
But the number of boxes is a constant.
Yes.
There
So
are multiplicities.
you have multiplicities. So here it's not a single point. You have many points stacked on in the same location. They are the same, but you should when you consider n, you count them as multiple points.
So can you remember why the ratio of the plus or the minus is constant?
No, we just assume that.
You just
Well, that's the ideal case. What I said is let's first solve the ideal case and try to, if we have time, we try to see how can we reduce from the original instance to the ideal case. Okay, so any questions? Yes. We still have some time. Let's briefly discuss how to reduce to the ideal case. So of course, at the beginning of the problem, the phi values can vary a lot. So it's not bounded by a function of epsilon. But you can use another shifting technique. But now it's not in the d-dimensional space. It's in the phi space. Not in the phi space, actually in the log phi space. For every point, you map it to one-dimensional space where its number is the logarithmic of the phi value. So you just essentially sort all the points from using their phi values, but those numbers are the logarithmic of those of the phi values. Okay, then imagine that now we partition this one-dimensional space into using a one-dimensional grid with say each interval has length say 1 over epsilon or something, right? So then, as you can see, if you have an interval here, say its length is 1 over epsilon, then all the points inside that interval will have, they have similar phi values. So I want to somehow say that I want to solve the problem in each interval individually. But this is, of course, seems not possible because
You have a lot of people. Plus you have a lot of intervals, right?
yeah, you can have a lot of intervals, that's fine.
Yeah.
But for each interval, if you can solve it individually, then it's still fine, right? Because in each interval, the problem you are looking for is so you are looking at is they have similar phi values. So the question is, how can you make each problem individual, so independent from the other problems?
Yeah.
So this is the main question. So if you can somehow make them individual, then you can do it.
Wait, why, even if you make them individual, how you can do it? Because the number of intervals doesn't depend from epsilon, right?
No, so how many intervals you need to consider? If the interval does not contain any point, you don't consider it.
Yeah, but you have n number of points, or not n number of,
Yes, but
n over epsilon.
okay, so each interval, suppose I have an interval which only intersects 10 points, then the problem size of that some problem is 10. Yeah. Yes.
Yeah, right.
So the total number, the total size of your
So you
problem.
have this like linear problem, and then you summarize
Yes.
the time of.
Yes,
Yes.
yes. So okay, but the key question here is how can you make the sub-problems individual? So the only case where why the problems are not independent from each other is that when you have those intervals, you can have edges which connects 2 points in different intervals, right? Now, what if you just remove those edges from your, suppose your optimal solution contains those edges. If you can show something like if you randomly shift your partition and then you remove those edges from your from the optimal solution, if you only lose by a epsilon factor, then you are happy. So it's the same as before. So we do shifting in d-dimensional space. But now, in order to prove it works, it's trickier. It's not that straightforward. But the basic idea is the same. You build maybe not 1 over epsilon.
Yeah, but I mean, it'll be very, very diluted. I mean.
Yes. So okay. So maybe I should use whiteboard.
Sure. Start writing.
So you have such a real line, right? So you have this is your one-dimensional grid. You randomly shift it. Okay, if you somehow know that in the optimal solution, all the edges are somehow short in this space, then still you know that the say it's of constant length, every edge has constant length in your optimal solution. Then you are happy because you know that so the distance here is 1 over epsilon or something, say 1 over epsilon square or something. So then you know that the probability that your breaking point will hit this edge is just epsilon, smaller than epsilon. So you only lose an epsilon fraction of the total length. So that case is the ideal case. But actually you can have very long edges. And for those edges, the probability maybe even like you have probably 1 to hit this edge. But the main so the main insight is the following. Look at this edge. Suppose this edge connects 2 points, x and y. So we have this edge, x and y. So this edge is long in this space, meaning that phi x and phi y differs a lot. Differs by, say, a large function, or its difference is larger than any function of epsilon. Then the insight is the following. You can remove this for free. Why for free? Because say y is larger. So when you remove this, the penalty you pay is at most phi x plus phi y. Right? But you know the edge length is at least phi y, and phi y is much larger than phi x. So what you paid is at most some epsilon times the length of this edge, which you can afford. You can charge to the length of this.
Yeah, but then, so then you need yeah. Yeah, I mean, when you prove all of it, you need to follow all your constants and all this.
Yes, that's
it's
true.
It's very hard, right?
Yeah,
To make everything work.
no, so you can remove these long edges at the beginning. So this is the first step. Then you only increase the opt of your solution by epsilon opt. Then you do this random shift.
Yeah, but you mean the distance between X and Y is very large, actually. So,
Yes, so no, as long as my phi y is say greater than or equal to phi x over epsilon.
so the distance between them is the 1 over F, so then logarithm 1 over F, right?
Yes, yeah, let's see.
No.
Yeah, it's logarithm.
Logarithm is F, logarithm of F.
Yeah, so I think if this one is
Log of phi.
yes, so. Okay, if this one is greater than 1, then that means phi y over phi x is at least 1 over epsilon, right? Because you are in the log space. Right? Yeah, if it's greater than 1, you can safely remove it.
What, one?
Can we please take this offline and let's.
Yeah,
let
so
you
there is
finish
just
that,
some calculation. It's not very difficult. Okay, so yeah, this is how like what we do to reduce to the ideal case. Yeah, so the argument is a bit trickier than before. So you need to handle those long edges. Okay, so finally, I pose some open questions. So the first open question is, of course, can you improve the quadratic time exact algorithm? Actually, the quadratic time algorithm only works for 2D. Can you, in 2D, can you improve that? Or in higher dimension, can you improve the cubic time algorithm?
Do you have a conjecture? What's the answer?
I think the answer is n square.
N squared?
At least it's very difficult to improve because for one-to-one matching, it's the best known exact algorithm is also n squared. And then I mentioned that we have this new algorithm, but it only works for the bichromatic case. What if we have more than 3 colors? And what about some more general matching problem? Okay. So thank you. This is my talk.